Hello again. So today we're looking at structural analysis and design made fun and easy. We're looking at structural concrete design to BS110. That's a UK standard. So we just got a simple beam. It's a single span with a small cantilever. So we're just going to work through finding the forces on the beam due to uniformly distributed load, and then finding the moments, and I'll show you the solutions and the question at the same time. So please like the video and subscribe to the channel for more content like this. So the question starts off with span, load, section of materials data. So we got concrete beam, concrete compressive strength equals to 30 newtons per millimeter squared. The reinforcement characteristic strength is 460 newtons per millimeter squared. The unit weight of the concrete is 24 kilonewtons per meter cubed. So sometimes you'll see, I used to see they give you the unit weight of concrete is 2,400 kilograms per meter squared. So it would be 2,400 times 10 divided by 1,000. So that will give you 24 kilonewtons per meter cubed. So in the question it just says, I don't know whether you can see it that well, but I'll just read it out because then you won't have to worry about reading the figure below. This diagram here, as I'm highlighting with the mouse, shows a reinforced concrete beam span A, B, C with an overall depth of 350 and width of 300. That is required to span 6 meters. That's to say the middle span is 6 meters. The middle span here is 6 meters from here that should be A to B, and it has an overhang portion BC of 2 meters. So this is A, this is B, this is C, this is 6 meters, and this is 2 meters. It supports a design load of 30 kilonewtons per meter at the ultimate limit state. So basically that means that the uniform load on the beam is shown in blue, 30 kilonewtons per meter ultimate, so no additional factor of safety required. But it does not say including the self weight, so I've added that on a little bit later on. The figure shows the steel reinforcement arrangement for the beam, and you may assume a cover of 30 millimeters to the length. So yeah, I've just drawn out the beam here, simply supported between A and B, and then the cantilever span is C, that's 2 meters. Simply supported between A and B, span is 6 meters. What I did was I drew section markers through the beam. That's section AA. So looking through the beam, it's rectangular. Got rectangular section 350 deep by 300 millimeters wide. That just illustrates the reinforcement typical, but it's not the actual reinforcement. The support is different. It's shown a bit further down. So the first thing the question says is determine the maximum design supports in the beam, which is 2 marks. So this question is 20 marks and it takes 36 minutes. So this is I work out that's 1.8 minutes per mark. So this gives you 3.6 minutes to just find out this quick calculation to determine the maximum design support moment in the beam. So we had before, I've drawn a part diagram of the beam at the top here, and we've got the UDL is 20 kilonewtons per meter over the length of the cantilever, and it states in the question it's factored, so we don't have to put dead load factor, but not including self weight. So the length of the cantilever is 2. Actually, I'll zoom in a little bit so you can see that bit. The UDL says W equals 20 kilonewtons per meter over the length of the cantilever. States in the question that this load is factored but not including self weight. So the length of the cantilever is 2 meters. Call that LC. The lever arm is a distance. Oh yeah, so first of all, before doing that, it's best thing to do is just to work out the total equivalent point load from the UDL on the cantilever. So I've just drawn that in orange as well. So the WC, big WC, called it big WC, which is equivalent total load W over the cantilever, is equal to 2 times, it's 30 plus the self weight, which is 3.53. So you get that equals to 67.06 kilonewtons. So actually, I'll just go back to this panel over here. The lever arm, the length of the cantilever is 2 meters. That's from here to here. So got a UDL. The orange section is it's the same UDL across the whole beam, but I've just highlighted the UDL on the cantilever as orange, and then the equivalent point load of the UDL over the cantilever is an orange arrow there, and that total is 2 times the little w. So so to find the moment at the support, which is B, we just got to take the equivalent point load, which is acting at the centre of the UDL load over the cantilever, and then times it by the magnitude of the total equivalent point load. So we need to find out equivalent point load and then the lever arm. So the lever arm, the centre of area of the UDL over the cantilever is 1, because it's just 2, the whole cantilever length divided by 2. So it's 2 divided by 2 is 1. And then we got, that's acting perpendicular to the beam. So the lever arm is just 2 divided by 2, which is 1. And the equivalent load is, it's just equal to 2 times the UDL. So the moment at B is given by the UDL over the cantilever times the length of the cantilever times the lever arm, which is the length of the cantilever over 2. So I quickly did a calculation to say that the self weight is equal to the width of the section times the depth of the section times the unit weight, which is 0.3 meters times 0.35 meters times 24, which is 2.52 kilonewtons per meter. And say the factor of safety for dead load is 1.4. So the W factored self weight, the little w that should be, is 1.4 times 2.52 is 3.53. So the total factored weight, the total factored UDL including the self weight is 30 plus 3.53, gives you 33.53. So when you go back now to WC, that's the total equivalent point load of the UDL over the cantilever. It's 2 times 33.53. So I've just said that again there. That UDL is applied over the whole beam. Just highlighted the orange section for the cantilever part. So very simple. Basically, the moment at the support is simply 33.53 times 2 times 2 over 2, and that gives you 67.06 kilonewton meters. So it's an clockwise moment applied at B. So we really should be it should be minus, but I'll just leave it as a positive sign, and it 0 at the C position, and then it's 67.06 at support B. So that equivalent point load acts perpendicular to the beam surface. So that's part 1 of the question. Then part 2 it says now we've got to determine the maximum design moment in the beam, in the span of the beam, design span moment in the beam. So that's 6 marks. So basically what I did for this was I redrawn the beam again, and we've got the UDL over the whole length of the beam, which I just calculated 33.53. That is that blue line is the UDL over the entire beam, including the self weight, 33.53. So the equivalent point load of that UDL is where I've drawn the is equal to, that's 33.53 times 8. So I'm going to use that in a minute to work. When I take moments about A, I'm going to use that equivalent point load to work out the support reactions using moments about A. Just to show as well, the little orange arrow I drew in the part A of the question. That is the moment at the cantilever, so you can just see that on there. So to find the support reactions and the moments in the span, easiest thing to do. So we just use the three equations of static equilibrium. So we got basically we know there's no horizontal forces, so equation 1 is not required. So I just called equation 1 the vertical. That's like all the forces acting in the y-axis. So the total RA, that's the reaction at A plus the reaction at B. Those are both acting perpendicular to the beam in the y-axis. That must equal to the total load acting downwards. So RA plus RB is equal to RA plus RB minus 33.53 times 8 equals 0. That gives us, if we just rearrange that, then we get RA plus RB equals 268.24 kilonewtons. I just write that in. So we want to find the moments in the midspan. We need the support reaction. So now we've got to take moments about A to find the support reaction. So basically we got we do moments. The first force that we're looking at is the UDL over the entire length of the beam. So we can take the equivalent point load, and that is acting at the centre of the load of the the UDL. So the entire length of the UDL is 8 meters. So we just it's obviously the same over the entire length. So the centre of load of the UDL is the length of the load divided by 2, which is 4 meters. So then we take moments about A. So that force going clockwise about A is 268.24 times 4. That's, just to say that again, it's the total UDL over the entire length of the beam at the centre of load, so it's simply 33.53 times 8, which is 268.24, and then times it by 4 meters, which is a perpendicular lever arm, and that must equal to 6 meters times RB, because RB goes the other way. So we got minus 268.24 times 4 plus 6 RB equals 0. So we rearrange this and we got 6 RB equals to 800 plus 160. Oh, yeah, sorry, it should be 6 RB is equal to 268.24 times 4. So that's just a little error there. That should be 4, because 4 times 200 is 800, and it should be 4 times 68.24, which is, it's 272, 272.96. I'll check that in a minute, but so 6 RB is equal to 1072.92. RB therefore is equal to, take the 6 down to the other side, 1072.96 divided by 6, which is 178.827 kilonewtons. So it's a bit of a weird number. If you do it without the self weight, you get 160. I've double checked that. So then that means RB is equal to 178.827, and RA, plug that back into the vertical equation, and you've got RA equals 262.26, which is the total vertical load down, minus RB up, minus 178.827, and that gives you 89.413 kilonewtons. So basically now we know what looking at our diagram, our moment diagram, I can draw a quick moment diagram now. We know that RA is equal to 89.413 kilonewtons and RB equals to 178.827 kilonewtons. So by experience, it's likely we've got a span here of 6 meters. We know that if this was simply supported without the cantilever, we just have WL squared divided by A. So from experience, I think that the moment will look something like this, with it starting at 0 here, and then we have the fixed moment of the cantilever, which we calculated as 60 there, and then between that point and that point, then it will be like simply supported. So we'll get a curving moment, but it will just finish at 60. Instead of finishing at 0 at RB, it will finish at 60 because that position is set. So just to check this out, I think the maximum moment will be at the midspan still. So we take moments about midspan to the left-hand side. So this is like the method of sections. Just cut the beam in half and then just look at the force on the left-hand side. So the moment about the midpoint of the span is equal to 3 times RA, and then that's clockwise. So sorry, I've done the signs wrong, but and then minus 33, minus the moment from the W, from the UDL, that's 33.53 times 3 times 3 over 2 times the lever arm. So I should have drawn another little arrow there so you could see the W, the equivalent point load from the W on this side, times the lever arm, which is 3 over 2. So that means that the moment, when you work that out, it's 3 times 89.43 minus 100.59 times 3 over 2. That gives you 268.2 minus 150.89 is 117.349. So that's the maximum moment at the middle of the span. So it's basically found out by doing methods of sections. That's the first method. And then if we want to check this, we can just take, if we cut a line down the middle of the beam, we can take methods of sections on the other side. Then we got maximum moment. Moment at the midspan is 3 times RB, which is anti-clockwise, minus the moment from the UDL over the beam on the right hand side of the middle of the span, and so that length between the middle and the end is 3 meters plus 2 meters is 5 meters. So then we got the moments equal to 3 times RB minus 33.53 times 5 over 2, which is the lever arm, and we got 3 times 178.8 minus 167.65 times 2.5. So that works out as 300 plus 236.481 minus 419.1253. So that equals to 536.48 minus 419.127, and we get 111.356. So I got it. Okay, it's not. I'm in the second decimal place. It's a little bit out, but so basically we've got 117.35 kilonewton meters as the moment. So just to go back and check, as I was saying, the second check, if the beam was simply supported, then the maximum moment would obviously be at the middle, and it'll be WL squared over 8. So in this case, we can just do a quick check. We know that the moment 60 here at the support B is 60, so at the middle it must be that triangle, it must be half. So the moment, the projected moment from the support is 30 in, that means that it would be tension on the top. If there was no UDL in the span, then we just have 30 at the top. So if we add, we know that position there is 30, then we know that WR squared would be would be 30, which is the W, that's without the self weight, 30 times 6 divided by 8. So that gives you 135 kilonewton meters. And the moment due to the cantilever projection is 30, so that gives you 105. So basically that's the same as 117, but without the self weight. So that's how I checked it. That's how I checked that it would be okay. This video is getting a little bit long, so I'm just gonna gonna make this into a 2 or 3 part video. So for the rest of this question, please, I'll link the next video into this video. But so in this video, basically we've worked out the moment at the support B is 60 kilonewton meters, or with the self weight that's 67.07, and we worked out that the moment at the middle of the span of AB is equal to 117.356. So in the next part of the videos we need to use those moments to determine the reinforcement that we require, checking the reinforcement and the shears basically due to those forces. We found the reactions of, we found RA and RB in this beam. RA is 178 and